Okay, so hello everybody. Hello Hannah, being here in person. So we're gonna do a little review session of Anova. So last time it was a little bit fast and a little bit much. Then there was the quiz in between, and I really need you to know the basics of Anova. So essentially, Nolan and Heinzen in their slides, they're basically talking about a one-way between groups Anova. So that's chapter 12. And then there's a one-way within groups Anova, which is chapter 13. And then there's chapter 14, which is a two-way between groups Anova. So I have decided we will stay with the one-way between and one-way within groups Anova. I will briefly talk about the concept of a two-way between groups Anova, but I have determined that at this point, this is beyond the scope of what you guys really need to know for an introductory statistics course. It's getting too complicated at this point. I just want to really have you come out from this class and really have a basic understanding what is an Anova. So we have a one-way between groups Anova, and essentially the way you would be applying this concept of an Anova for between groups, you would have more than two groups. So when you have two samples, it's easy, right? You do an independent samples t-test and you compare these groups. You have a before and after sample, you have two separate conditions, you have a dependent sample, a matched pair sample, and you basically do a paired t-test comparing both before and after conditions. So now basically with the Anova, it's nothing else in essence. You have a one-way between groups Anova, you have like a third sample, right? You want to test the difference between the third sample and you want to test the null hypothesis that this sample is not significantly different from the grand mean of all three samples. And when you have a one-way within groups Anova, you have nothing else but more than two conditions. So you don't have just before and after, but you actually have before, after, and in between. And you want to compare these three. So essentially a one-way within groups Anova is nothing else but that. And all what we're going to talk about is essentially how to practically approach that. And well aware that the calculations for that are tedious and they're a little bit of an overkill. And I repeat it at this point, what you really need to know down the road for finals, I will not ask you to calculate every step of an Anova at the finals. This doesn't make any sense, right? So what I really want you to know and keep in mind is that you know how to analyze and how to interpret an Anova table. And we will talk about how to put that Anova table together. You have it in your Excel spreadsheet. And I will want you, and this will be on the finals, that's for sure on the finals. You will need to know what does each of the columns of an Anova table mean, and how can I, if I have a blank on one spot, how do I calculate it? If I have, for example, and let me quickly put this in. So this is what I prepared for today. And this is what you know from last time, right? So last time we populated this Anova table. And essentially what I, for example, would ask you at the finals is like, okay, so you have the between and you have the total, what's the within sum of squares? Or you have the mean squared, you have the sum of squares, you have the degrees of freedom, calculate everything up to the F. So like I leave you blanks, you calculate up until the blanks. And I don't think this is particularly hard, and I don't think this will be much of a problem for you to tackle as a challenge on the finals. So, but these are kind of the things you need to expect for the finals. I will not make you go through this entire calculations here because that's essentially, I believe, an overkill. Okay, but now back to the Anova principle. So with the Anova, we're introducing now, in addition to the C distribution and the T distribution, we're now additionally introducing the F distribution. So the F distribution is what you know, as you know, when you work with three or more groups, and essentially you use it with one or more nominal independent variables. The nominal variables are those that are not ranked, as you remember. The ranked ones are the ordinal ones, and the nominals are those where you basically compare three different nominal variables. Like You would, for example, driver alone condition, passenger condition, video phone condition, cell phone condition, and you compare the response time, so you compare the likelihood of a collision. So these are these kind of questions you would be looking at, where you're on the y-axis, on the dependent variable axis, you essentially have a scaled variable, whereas on the x-axis you have nominal variables. So the reason, and this is also, I flagged this for possible quiz question or finalist question, why not use multiple t-tests? Is a reasonable question, right? It's like essentially you have three groups. You can compare 1 versus 3, 2 versus 3, and 2 versus 1 versus 3, 2 versus 3, and 1 versus 3. No, you don't need that. Oh, you need 1 versus 2. 1 versus 3, 2 versus 3, 1 versus 2. So this would be 3 t-tests that you can test, right? So the problem with 3 t-tests is that every time you're running this t-test, you have the same type 1 error probability. So these 5% of alpha are going to be present with each of your tests. And this is just adding this up for 3 groups. Essentially, you're ending up with a probability of a type 1 error, which is just unacceptable for your hypothesis testing. So for this very reason, you're testing with the Anova. Okay. With the Anova, you essentially, so we talked about this with the sample, with the Anova, you test the null hypothesis that the mean of all groups are not significantly different from the grand mean, from the overall mean of all 3 groups, of all other groups, no matter how many groups you use. So this is the null hypothesis here, and I'm looking for the null hypothesis here. Okay. So here are the types of Anova. So the hypothesis test includes 1 nominal. Okay. So I'm thinking of the other slides. Sorry for that. Okay, so essentially we are testing the hypothesis that each of the group means none of the group means is significantly different from the grand mean of all 3 groups. So this is what you're testing, and you essentially are testing that by testing the variability to compare those means, because as we remember from the effect size is determined by the difference between the means and the variability of the respective populations or samples. Not necessarily populations, no, it's the samples, right? The variability of the samples will determine whether the effect size is great or not. And this overlap between both samples will determine the power. So the greater the overlap, the smaller the power. So when you're calculating now the variance between the groups and you divide it by the variance within the groups, you come to the F. And this F, once it exceeds a certain threshold, and this is treated as a two-tailed test. So you're not multiplying the p-value by 2. You're treating it like a two-tailed test, but you're testing it only in one direction. So it's a one-way, it's a one-tailed test disguised as a two-tailed test. Let's put it that. So essentially you're testing it along your F distribution. And there is one very good slide. So you're testing it along your F distribution. And while you're using a 5% p-value, you're only testing it against the null hypothesis of exceeding this F of 3.86 here for this particular example. So this is, you will always read this from the so-called F table, and you will have the within groups degrees of freedom, and you will have the between groups degrees of freedom. So for the example of our last Monday's class, we are, okay, so there's some assumptions which you essentially have to meet, which is a random selection of all the samples. it's normally distributed samples, and it's further homoscedasticity amongst the samples. Homoscedasticity is, this is a very complicated word, and I'm well aware, and don't ask me how to actually break it down, because it's Old Greek. But essentially what it means is that the sample variability between the groups does not differ more than a certain amount or threshold that you set. This, in essence, is as a rule of thumb, and I'm just telling you this now, this is not material for the finals. As a rule of thumb, it's not supposed to be more than double. So you're not supposed to have more than double of the variability in one sample as compared to another one. There are tests. There's a test named Bartlett test, how you can test this homoscedasticity, but it's not advised by statisticians to really do that. So what are we doing now? So we have those assumptions. We have random selected samples with normally distributed samples. Homoscedasticity, we want to compare our example from class was, okay. So from 15 society, we're selecting samples, and we have 4 different conditions. We have 4 different nominal groups. We have the foraging societies, we have the farming societies, we have the natural resources societies, and we have the industrial societies. From those, we're playing a dictator game with them. In the dictator game, basically, the dictator has the right to determine the proportion of money he would give to another person, and the fairer, so the more he gives, the fairer it is. And essentially, that was used by the researchers to determine whether a society has a higher fairness score or not. So we went through this, right? So we calculated all of this. So we have here a fairness score. We have fairness score values for the foraging society. We have fairness scores for the farming society. We have fairness score for the natural resources society and for the industrial society. So the first thing you essentially do is you need to calculate the total variability. So this sum of squares total is possible first step. So essentially you need to calculate the so-called grand mean, which is essentially the average of all entries. So you're pooling all the entries, and this is what I did here. So that gives you this grand mean. As a next step, you essentially calculate the total variability. And the total variability is the sum of these squared differences. So in the first step, you're taking each x and you're subtracting the grand mean, which we have here, so the 9.38, from this x. This gives you 4x's, 3x's, 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 gives you all these differences. Now, next step, you square these differences. Squaring these differences will give you the squares. And now in the last step, you're just going to calculate the sum of all squares by summing all of these up. And that's already all you need. That's already your sum of squares and comes directly into your Anova table. So, secondly, you want the within variability. And the within variability, the within sum of squares, essentially is calculated on a group level. So you have this overall level. You subtract the grand mean from each x. This is the total sum of squares. Now you have the within sum of squares, and within you need a mean. You need a group mean, right? So you calculate the group mean for each of these groups. You subtract your x, your respective x, from this mean, and you end up with the differences. And just like with the total sum of squares, you're squaring these differences, and you come to calculate then the sum of these differences of the squared deviations, and you get the sum of squares within. And this is, again, everything you need. This is your within sum of squares. And you can bring this down to your Anova table. So now, lastly, you can essentially, well, if you want to calculate the sum of squares between, you can essentially do that by calculating the m minus the ground mean, gives you difference. Squaring this and multiplying it by the number of degrees of freedom within that group gives it a weight, and that's why you need to multiply it by the n. So essentially you get here 150, you get 57, you get 63, you get 189, and the sum of that is 461. So now, however, if you have 461, and this is where it's getting interesting for the calculation on the finals, for example, the 461 is also nothing else but the total minus the within. So you can essentially calculate this easily by just calculating the difference between total and within. So, for all this being known, now let's move on. And the Anova table, what do we have next? So we have the degrees of freedom. So the degrees of freedom for the between is the number of groups. Is the number of groups minus 1. If we need the within number, we have to degrees of freedom within is the degrees of freedom. This is what I'm showing. Go back. So here we have the degrees of freedom minus the number of groups. So this is a degree of freedom between minus 1. And we have the degrees of freedom within. So now we have degrees of freedom for each of those groups. We need to pay attention to the actual degrees of freedom with the sample size. So here we have a sample size of 4, degrees of freedom of 3. Sample size of 3, degrees of freedom of 2. So we essentially have 3, 2, 2, 2. So this is 6, 2 by 3, plus 3 is 9. So this is how we get to degrees of freedom of 9. Now we have a total, just summing this up, of 12. And now it's easy to calculate the mean squares, the MS, by just calculating the sum of squares between and the sum of squares within divided by the degrees of freedom. And the actual F is being calculated as K40, which is here the between mean squares divided by the within sum of squares. And by this you get 8.27. Looking this up on your F-squared table, which is this. Okay. Looking this up on the F-squared table, so we have within groups we have 9, right? Between groups we have 3. So essentially 9 and 3 comes to this group. We want the alpha level of 5% is 3.86. With an F of 8.27, we're rejecting the null. And we know that there's at least one group is significantly different from the grand mean. So we're calculating the F. We're getting these differences. And each of those groups has variability within and there's variability between the groups. We're having this Anova table. Nicely explained here. In that example, we did order calculations. And we essentially order. So we basically have filled all of this out. If we go further down, we have 8.27 and the cutoff is 3.86. We are rejecting the null hypothesis. We're going further down. And now we're coming to a point which is a tricky one, which is the so-called effect size. I wouldn't call it an effect size. I would refer to it just simply as the R squared. And the R squared, it serves as an effect size for the ANOVA. I agree there. But essentially what it is, it's nothing else but a proportion. It's a proportion of the variance in the dependent variable that is accounted for by the independent variable. So now we haven't spoken yet about correlations and regression, and we're going to get through this after the Passover break. And that's why I want to conclude Anova with today, because we're coming in an entirely new world now. And it's an exciting world. It's actually one of my most favorite topics. It's really going to be fun. You're going to like that one. So R squared is basically a concept that comes from this world. So essentially what it is, you have the sum of squares between. So you have the sum of squares between the groups. And this is the part of the sum of squares in total that will determine your effect size, your quote-unquote effect size. So what this essentially is, since it's a proportion, it's a value between 0 and 1. And it will determine the strength of your association. And yes, it will be associated with your F. So the higher, the greater your F, the greater your R squared. But essentially it serves as a marker of the effect size in the example of Anova. And we'll get to the details. We will get to the details later. So the convention again, there's a convention of a small effect size, a medium effect size, a large effect size. 0.14 would serve as a large effect size, 0.01 as a small effect size. So we have with 0.73, we have a fairly decent effect size. So that means that the rejection of our null hypothesis actually was quite highly significant. So, and now we're coming to the point. Okay, so initially I said like, okay, so you need the ANOVA to not have to do 3 independent t-tests, right? But now in the so-called post-hoc tests, we're doing exactly that. We're doing an posteriori. So I don't know, you may remember from philosophy in high school that there's an a priori and an a posteriori. So this is very, this humanistic principle of theory expression. And you essentially, have 2 approaches. You have an a priori approach, where you plan an approach. So if you, for example, you say, okay, so I have an ANOVA that I want to test and those 4 societies, but I have already a preconceived idea that one society is going to be less fair than the other, or one is going to be more fair than the other. So I have an a priori comparison already in the back of my head. And I will plan this out and I will add this to an analysis plan. Then you can do this analysis. After you did your ANOVA and you found that there are significant differences, you can do this a priori planned comparison. Secondly, what you can do is post hoc, where you do post hoc, which is also the a posteriori. Posterior means it's done afterwards, where a priori is before. So prior, a priori, posterior is post the event, post hoc. So essentially, it's really that easy. And this is where things kind of merge with Latin and the etymology of the English language as well. So this post hoc test is post an event. So the post hoc test essentially is the comparison of groups when you know already that your primary hypothesis was rejected at an alpha level of 5%. So you know at an alpha level of 5% that your null hypothesis is wrong. So one of the groups is going to be significantly different. Post hoc, you can apply now 2 different are mentioned here. There are a plethora of others. So there are more. But Tucky the Taki honest significant is actually one of the most popular ones. The other one is Bonferroni. And Taki's honest significance testing essentially is using kind of a principle that we know already. So it's basically, it's a mean 1 minus a mean 2 divided by the standard deviation, where the standard deviation, the standard error is determined by the mean squares within divided by the n. So essentially that will lead you to this so-called Q, to this critical value. You will do it, in essence, what you will do, you would use the Anova in a format in a statistical test. So this will not be something you often calculate by hand. So you have this Q table, and again, we have the within groups of freedom of 9, and we have degrees of freedom of 3 at the treatment level of 3, number of groups. We have Q of 3.95, which is the critical value, and calculating it for Taki. We could do that now, but I don't think there's much purpose at this point to do that. Bonferroni, I just need you to understand the concept. So Taki essentially uses the Q statistics, calculates essentially the difference and divides it by the standard error of the mean, and the standard error of the mean is calculated based on the variability within the group. So that's all you need to know from Taki. From Bonferroni, this is another post-hoc test which wants to account for the fact that there was multiple testing involved by essentially reducing the critical value. So you're dividing the P threshold that you're willing to accept, so which is the alpha level of 5, right? So you're dividing that by the number of comparisons. So if you take an alpha 5% and you divide it by, we had 4 groups, you divide it by 4 groups, you come to a p-value of 1.25. So which means that your resulting p-value needs to be at least less than 1.3% for you to accept the null hypothesis of this group being different. So you would do those 3 comparisons. Actually, it's divided by 3. Sorry. It's 3 comparisons. 4 groups, it's 3 comparisons. So essentially, you would compare them. No, it's actually, hold on, 1 versus 5. Okay, no, it's actually more. It's n plus 1. If you do 5 comparisons, that versus this, that versus this, that versus this, this versus this, this one, yeah, this is n plus 1. Yeah, so it's actually, yeah, 5% divided by 5. So it's actually less than 1%. Okay. Okay, didn't think that, but I should have done that before lecture. Okay, so we do a post-hoc test. So we're basically using minimized critical p-value that you're aiming to reject the null hypothesis. And so essentially by the number of comparison, you're actually lowering this substantially down until you essentially need a very highly significant comparison, essentially, to reject the null. And this is all of this, essentially. So those that are listening in, are there any questions? Simon, Notaro, Hannah? No? Okay. Okay. Because now I wanna move on to the one way within groups comparison quickly. I just meant to quickly review this to make sure that we're all on one page here. So the one way within groups. So I mentioned it already in the beginning. So the within groups essentially is nothing else as comparing before, within, and after situations. So you have same subject giving you repeated answers to different questions. It's a dependent sample, right? It's the same person grading the same thing. So essentially that also is going to be the example we're going to be talking about, just to illustrate that Okay, so this is the calculation here. I will post this here too. So this is what we're going to calculate now. So we have here, we're going to be talking about Bush. We're going to talk about beer. So Fellows wanted to know whether his recruits could distinguish amongst widely available American beers that were categorized into 3 groups based on the price. So we have the high-end beer, we have mid-range beer, and we have cheap beer. All these beers are lager, they were found for a certain reason, and the mean scores are scaled on a scale of 0 to 100 for each category of beer. We're looking at 5 participants that are doing this comparison. So we have here the data. So we have participant 1, 2, 3, 4, 5. We have cheap beer, the scores of a cheap beer. We have the score on a mid-range beer. And we have the score on a high-end beer. We have these values right here. So we essentially, what we want to do now is to calculate based on that whether there are significant differences between the groups and within the subjects. So for this very reason, we get a new Anova table. We're expanding the Anova table. Now we have the between groups, as we had before. We had the within groups, just like we had before. We had the total sum of squares. And now we also have the subject level. So the subject level essentially gives us a new dimension, which already emphasizes that we need to account now for the subject level. And this we will do, firstly, by reorganizing the data level. So now we have had the format of, which is called a wide format. The wide format is not a very commonly used format. Essentially, in my world, we barely never use the wide format. We're using something that is called the long format. And I will show you that on the calculations total SS, on the calculation of the total sum of squares. So let's start with this off. So what we essentially do in my world, we're using now the long format. And the long format, you basically have for each entry a certain characteristic. So you have here the cheap beer, you have a repetitive identifier for cheap beer type. So you calculate all of this, and you arrange it in a way that it's long.
Mr. Ryman?
Yes.
I have a question. For 12, for the variance.
Okay, so now we're back at it. Okay, so we have the mid-range beer. We do have the high-end beer. And we're basically reorganizing this data in a way that we have it in a long format. And this long format is quite important in this context because it's the first time we're basically doing some more high-end statistics, and the repeated measures Anova. That's a synonym actually for this test. It's a repeated measures Anova. So I think part of this course also should introduce you terms you will be exposed later on in your careers. And repeated measures Anova is something you will hear quite frequently for some certain tests and some certain analyses. So repeated measures Anova, essentially you have repeated measure for participant 1 to 5, tasting different beers with different scores. And this being said, you do nothing else in the greater picture than what we did in the past for the within between group Anova. So you calculate first the current mean, which essentially is nothing else but average. of the whole thing, which is here 40.533. You calculate x minus m, no, minus gm. So your x minus gm is essentially here this x minus this chromine. Sorry about that. Minus this minus this. Okay. Because it's interesting because as soon as the schema is green, it kind of reacts delayed. And I kind of time for the slip. Okay. So now we have this list of differences. And if we scale this up now, x minus gm squared, we're basically getting the squared deviations again, right? So these squared deviations will then allow us to get our first sum of squares. Equals sum of squares. So we're summing all the squares, we get now that value, which comes now into our total. This is our total sum of square. Okay. So now we need another one though. What we need now is the between groups. The between groups difference, sum of squares, sum of square between groups. So now we're calculating this again. And what we need now is, let's take a different color just to be distinguishing this. Okay, so what we need now is something which is a GM, a group mean, as we had before. So this is now an average of all the GPUs, all the GPU responses. So now it's a little bit more complicated now because you need to take this $sign to basically log all your responses. But you get a handle on it. So take this one down. It's now W8. W7 to W. Is this 11? Yeah. Okay. That's 34.6. That was already. So this is already the group mean. So you can compare already with the naked eyes. Like it doesn't matter that much, right? It doesn't seem to be much of a difference here. But now we're going to come to the high end here. So let's see how much difference that could be. Now we do W12. Until 17. Okay. 5 to 16. Okay. So here we're already seeing, right? This is the scoring of the beers. So the high-end beer, they really like the high-end beer. So this is our grand mean. Now we do nothing else but m minus the mean, so the respective mean minus the grand mean. This is the within group. Okay, so this is the between group. Between group. This is between group. This is okay. So we have a mean. We have this. This is the. But this is not the grand mean. Sorry for that. This is the normal mean. This is the group mean. This minus this. one of the reasons why I'm also showing it in this clumsy long format is because the sum of squares and the actual count, you need to count this for each individual. So the degrees of freedom overall are not changing. So this sum of squares needs to be calculated exactly in that format to come to the sum of squares, right? Because it's a sum, it's not an average. So the number of entries are actually very important in this context. And this was, of course, wrong because I need to first square it. Okay. So this is a square. But then not this squared. This is a relatively large number. And we're adding this up. And we're doing this as a sum. Okay. Sum. Okay. 1092 and 13. And this is in cell C18. Groups equals C18. Okay. So now back to our calculations. So what are we doing next? So now we're going to do something different because we need, as the next step, we need to have the between subject. We need to have the within subject estimate. So what does this mean? Okay. So let's do this one down here. Okay, between group. We're going to do now another further. Okay. We are now doing X. So we're doing subject mean, participant mean. What's the participant mean? We're doing X minus participant. It's the participant mean is PM. Okay, so everybody please remember this is our participant mean, X minus PM. Okay, so now we do a participant mean. What is the participant mean? This means that this is the average of each participant. So we have participant 1, participant 1, and participant 1. So this is the participant mean. So the participant mean is basically each response that participant gave to the question. So if we do an average here again, this is for participant 2. Okay. And this is participant 2. This is again average. Average 1. Okay. Okay. This is fairly easy. So I think you get the gist of it, right? You basically just building. Obviously, you can imagine statistical software. It's super easy to do that. Yes. Okay, back at Anova. Okay, so we have now group subject number 4. Now we have the average of subject number 5. And so we're going to be finished. So subject number 5. We really like the high-end beer. Okay, so now we're looking at this. Okay. Okay, so what we need to do now is a little bit tedious. Just bear with me, because we need to log everything now with the dollar sign. Otherwise, it's going to shift as soon as I copy it down to the other entries. And I'll be done with that in a second. Just keep in mind, in case you ever come in the situation later for your thesis, final projects, or whatever you're going to do down the road, there are easier ways for doing all of this, and you will probably find your own ways to do all these things. I'm not necessarily doing it in the fanciest approaches that I would know how to do, but it's like sometimes the easiest way is the easiest one to show things. So we have, I'll just quickly double check a couple of things. That's interesting. This one, 28, 28. This way. This way, 28. Okay, there's a typo now. Something was not going right. Okay. Okay. So now we're coming from this participant mean now. Yeah. How did I manage that? How's that impossible? Bear with me for a second, please. I'm a big Apple fan, but the mouse is really not liking me today. The problem is because it's okay. Okay, we're back now. It's a beer. Sorry for that. It was just really tricking me for a second. So now we have, so we need to calculate now the difference between one entry minus the minus equals this minus this, right? Nice wrongs. Actually, it's the calculation of this minus, I'm getting confused, minus, it's the subject, the participant mean. So it's our PM minus the ground mean. Yeah, so this is how we're getting. And we are not summing this, but we're summing this. we're doing now this squared. Squaring this up. Okay, so now we have this squared. This will now 0.22. Going all the way down. I'm summing this up. Okay. Here we go. And this is our between group. Definitely off here. I have it off. Okay. Look at the lock tab on. Okay. So here we go. Okay. So we created now a participant mean. We're subtracting this participant mean from the grant mean. We're squaring this participant mean minus grant mean difference. And we're getting to a sum of squares for the subject. And this is our sum of squares for the subject. So, and now, you will probably guess it already. It's actually fairly simple to just calculate the within subject sum of squares. Because now this is essentially, and you will see this here, actually. Okay, so this is reduce. Okay, so the paired samples t-test. So this is the paired sample t-test question. So you basically have y1 minus y2, y3. This is the responses of the individual. You have the same sum of squares. The sum of squares within are subjects within the between groups. You get to this calculation, you get x minus the ground mean, you get the group mean minus the ground mean. You get the participant mean minus the ground mean, and you get sum of square total minus sum of square between minus sum of square subjects equals sum of square within. That's total minus everything else. And this is, I'm flagging this for the for the finals. Know how to fill those blanks. So this is the sum is total. The between, within, and subject is what adds up to the total. So between, how many degrees of freedom do we have? We have 3 B's. Degrees of freedom is 2. Within, how many subjects do we have? We have, look at the formula. Let's look at the formula. We have between n groups minus 1. Subjects n minus 1. So we have 5 subjects, which is 4. So how much do we have? We have between multiplied by subject is within, right? So it's the degrees of freedom between, which is 2. Degrees of freedom per subject is 4. That is 8. So now we have 14 degrees of freedom. So now it's also easy to get the mean squares, because the mean squares is nothing else but this divided by the, not this sum of squares, the sum of squares divided by the degrees of freedom. That's your mean squares. And the charm of this whole analysis is that you have total is n total minus 1. Now we go down. We're getting now all these calculations. And when you now want to have the f between and the f subjects, you gotta calculate the mean squares between divided by the mean squares within.
Thank
you. Get 2. You're welcome. So you want the between minus the within divided by the within. Between, just like the previous version, right? Between divided by within. This is your 14.8. This is your F1. N as subjects divided by within is your F for subject. Subject mean squared divided by within. is 4.94. And this is your F statistics. And your critical value now, let's look that up. Your critical value now, make a decision, yeah. That's the F table. Okay, let's search for the F table. They have an N here, I know that. Not that. Not that. I'm not that. Okay. Okay. You really do not have one, because that is very confusing. But let me tell you that the critical value is 4.46. We're basically rejecting the null hypothesis, and I'm not entirely sure that it's not F table in there. That doesn't make any sense. F and that is absolutely unbelievable. Absolutely unbelievable. Okay. Okay. So we want between groups, right? Between groups and subject. Between groups is 2. Subject is within is 8. 2 and 8. So a critical value here is 4.46. Just like stated here. The R square is calculated as we know by the explained variability. The explained variability divided by the total variability.
I only have 7 minutes left and I'm not going to finish.
Okay, I'll give you guys more time.
Thank you so much. And also, can I go use the bathroom?
Okay. Okay, so this is basically how you approach to within Anova, to within group Anova. And just some final words on how to approach this. So you basically, yes, so we've seen how to calculate the statistics. We know how to calculate the effect size. So we're doing S between divided by the S between divided by the subject, the total minus the subject variability. And by that, you're basically taking out this inter-subject variability. And you're getting to your R square. You basically yeah, so you basically calculate then again the standard error of the mean by calculating the mean squares within divided by the n. You can again do the Tucky honestly significant testing. And yeah, I'm not going to talk much about this. But this is basically how you do the within group Anova. And I think this is, it's very comparable to the between groups Anova, but I think it's quite central to understand because you will be facing a lot of research where you basically have several subjects that essentially participating in your research. and giving you answers to various questions. So I think it's very important for you guys to know the ANOVA. Whereas the two-way and three-way ANOVA, I personally think that this, for an introductory statistics course, is somewhat too much, because what you do with the between group ANOVA, and I just can quickly open up the slides to show you, essentially what you do with the between groups, two-way between groups ANOVA, is you come already in the realm of hypothesis testing, looking at associations. So essentially, this absolutely terrible acronym that they're using here is independent variable and here the dependent variable. So never use IV and DV. This is an absolute terrible acronym. So essentially, it determines individual and combined effects of variables on each other's, and it basically tests for something that is called interactions. So interactions are basically when two independent variables have an effect in combination that is not seen when looking only at one. Meaning, think of it as a triangle that is basically forming, and they're both affecting together one common determinant factor, one dependent variable. So essentially, you have blood pressure and blood glucose, for example, and blood pressure is affected by blood glucose, and then you have a third variable, you have age. So age will more likely affect glucose, age affects blood pressures, but age and glucose together, it basically indicates a diabetic, and basically by that indicates stiffer vessel walls, and then together they become this really strong factor determining the blood pressure. So this is just an example. So there are several examples like that, and I believe it's a little bit too far, but keep in mind what a two-way group between groups ANOVA does is it tests for associations and interactions. So you have two-way ANOVAs that includes two nominal independent variable and a scaled dependent variable. Then you have factorial ANOVA uses one scale dependent variable, at least two nominal independent variables, and you have factor. A factor is essentially nothing else but an independent variable. Yeah, I think this is also an important one to memorize. So you have, and I have this in the Excel too, which I will upload later. So we have a one-way between groups ANOVA. We have a two-way between groups ANOVA. So this is basically the number of independent variables are reflected by the one-way, two-way, or three-way. The participants in one or all samples is determining whether we have between groups, within groups, or mixed design. So between groups, within groups, mixed design, it's kind of a self-explaining kind of situation. So we have one-way, two-way, three-way. This is one way would be the societies, right? You have one-way society. You have a second variable. You have income status within that society would be a second independent variable. Three-way variable could be health status as a third variable. So there are many ways, many levels, many factors that could factor in. Between group means it's the same individual in one group, and it's a different individual in another group. Within group means it's one individual, either different time points, reacting to different questions, reacting to different situations. So it's within groups, there's the same subject, especially a center of intention. Then you have a mixed design, where you have a mix of all these components. And so this is basically how you assemble the one-way within groups, one-way within groups, two-way within groups. So this is the nomenclature used for ANOVA. So I think this is important at this point. I will upload these slides. I encourage you to have a look at it, but I will not be testing this in the funnels. And yep, okay. So this is the review of ANOVA, and I hope you found it helpful, and it gives you a good head start for the finals. Thank you very much. Are there any questions? So Atara, I see you joined. Thanks for joining. You have any questions?
Not really.
No? Thank you. Thanks for joining. Hope you found it interesting. Okay, so we'll pause the recording now. I will stop the recording now.